Hello everyone, and welcome to the second part in my talk on the description of domains of discontinuity for Anosov representations. In this part, I want to explain how one can show that some domain of discontinuity associated to Anosov representation are fibered. So what I want to is to give a proof of this theorem, which is not the one from the original paper, that if we have a representation rho that is each in PSL2 and R from a surface group, and if we take M, the quotient of the domain of discontinuity I described last time, it is a fiber bundle over the surface, and it's with fiber this Stiefel manifold, which can be seen as the intersection of two quadrics. And so I want to explain an argument for this theorem, a proof of this theorem, that can be generalized to some other domain of discontinuity and some other Anosov representations of surface group. So today we'll fix the surface group, but we might vary the Lee group. So first I want to do a first remark. If we have considered rho zero, to define each representation, we considered a representation that can factor through the irreducible representation from PSL2R and PSLNR by a Fuchsian representation from gamma G to PSL2R. So such a representation rho zero is called a generalized Fuchsian representation. And each representation are continuous deformation of these ones. But it turns out that the quotient of the domain of discontinuity for rho zero is diffeomorphic to the quotient for rho. So the topology of the quotient is not varying if you vary the representation continuously or smoothly. And hence, it's sufficient to just consider rho zero to prove our theorem, if we are just interested in the topology of the quotient. And hence, this problem is more about generalized Fuchsian representation, which are some very specific representation that factors from some PSL2R. So the technique we will talk about will mostly generalize the situation when your representation factors through a PSL2R. So I want to say a few words about symmetric spaces. So let G be a simple Lie group, or we could have semi-simple, but for simplicity, let's take simple, a finite center and no compact factors. So for instance, we can take PSLNR, and let X be the associated symmetric space, which is G mod K. So in our case, PSLNR, it's PSLNR mod out by its maximal compact subgroup, which is PSONR. And concretely, it can will describe the symmetric space as a space of scalar product on Rn, with a condition, since we have we consider SLNR, that the volume of Q is equal to 1. And so the tangent space at a scalar product Q of X can be identified with a space of U endomorphisms from U endomorphisms of Rn, which are Q symmetric, and the volume condition translates a trace of U is 0. And so in general, X is a Riemannian manifold on which G acts transitively by isometries, and it has sectional curvature non-positive. It's a cat, and it's a cat zero space. So this space is cat zero, but it's not strictly negatively curved. So it admits some maximal flats. The dimension of the maximal flats is by definition the rank of X. But all these maximal flats are isometric to a model flat F. So one example of a model flat F in our example of PSLNR is a space of scalar product whose associated symmetric matrix is diagonal in a fixed basis. That's our model flat. And given a point O in F, we define A as a tangent space at O of F. which is a model tangent space to the model flat. So in our case, A can be identified with the space of diagonal matrices with sum of lambda I equals 0. And so we have a discrete group called the Y group that acts on the model flat on A. So the Y group is the space of elements that stabilize A, modeled by the space of elements that fix pointwise points in A. And so it is a discrete subgroup generated by symmetries along some lines. So in case of PSL3R, I represented A, and the Y group is generated by symmetries along these three green lines. And the Y group has a fundamental domain, which is called the model Y chamber A+. And so in our example, this is A+. And in general, to have A+, we ask the same thing, but we ask lambda 1 to be greater than lambda 2, etc., until lambda n. Okay, so the model Y chamber is important to understand the geometry of the symmetric space, because to any vector v in the tangent space of X, we can associate an element in the model Y chamber, unique. And so to do this, we take any vector v, any such vector, one can find a flat f prime that contains v, and via an element of G, one can always map f prime to the model flat f. And one can map the base point x of v to the base point O of f. And so then up to acting by the Y group, one can assume that the vector v lies in A+. And so two vectors v in Tx can be mapped to one another by an element of G if and only if they have the same Cartan projection. So now, since we have a cat0 space, we can talk about the visual boundary of X, which is a space of geodesic rays from R+ to X, where two geodesic rays are equivalent if they are at boundless distance from one another. And the space of G, so G does not act transitively on the visual boundary. And the space of G orbit is actually in bijection with the space of points of unit vectors in the model Y chamber. And so these G orbits in the visual boundary of X are called flag manifolds. And they are called this way because often they can be interpreted as manifold of flags or Grassmannians. And the flag manifold associated to P will be called FP. To get the flag manifold associated to P, you look at all the geodesic rays so that gamma dot has Cartan projection equal to P. So an example in PSL3R, I have three vectors, unit vectors in the model Y chamber. And so the first one is associated flag manifold, is just RP2. The third one is RP2 dual, which is the space of hyperplanes in R3. And any vector in the middle, its associated flag manifold will be the space of full flags in R3. So sometimes for two different P's, the flag manifold can be diffeomorphic, but they are not the same in the visual boundary. So now, once we have points in the visual boundary, we can define Boozman function associated to them. So this can be defined in general for cat0 spaces. And the way we define this is we want to get the distance between X and our point A in the visual boundary. And to do this, we look at the distance between gamma of t and X, when gamma of t is a geodesic converging to A. But since this goes to plus infinity, we need to remove the distance between gamma of t and a base point that we chose O. And this always converges in cat0 spaces, and this will be by definition the Boozman function based at A, associated to A based at 0, at O of X. So the choice of a base point, it matters, but not always, not so much if we are interested in variation of the Boozman function. It doesn't matter because if we change a base point, we only change a Boozman function by a constant. And Also, an important property of the Boltzmann function is that the gradient of the Boltzmann function is equal to minus the vector VAX, which is a unit vector based at x pointing towards A. So that's the geodesic starting with this direction is in the class of A. And so these functions are natural functions, so they have nice interpretation in many cases. And so, for example, if Fp is identified with Rpn, so in the case in Rpn minus 1, if we take a line in Rpn minus 1, one can describe what is a Boltzmann function associated to the line based at the scalar product of another scalar product. And this is up to a normalizing constant lambda equal to the logarithm of Q of VV mod Q0 of VV, where V is any generator of L. If we multiply V by lambda V, it doesn't change this formula. Okay, so now we can go back to Hitchin representation, and the property of Hitchin representation, or more generally of generalized function representation, more precisely, is the following: if we have the irreducible representation eta, it preserves a total geodesic surface H in X, and this total geodesic surface is isometric to H2, and eta induces an identification between PSL2R and the isometric group of this H in X. So preserving isometric group of H in X. So in general, if we assume that rho from gamma G to G preserves the total geodesic H2 in X and act properly on it, so this mostly this occurs when gamma G factors through some PSL2R or some cover of PSL2R into G. And so we are going to consider this situation. We want to understand the domain of some domain of discontinuity of our representational rho in this situation. So what we want to do, we want to try to project. So we fix a P in SA plus. So we choose a flag manifold in the visual boundary. And given A in the flag manifold, we want to define its projection onto this total geodesic H. And to do this, what we want is to find, for instance, one way to define the projection would be to find a point which is closest to A. It doesn't make sense because A is at infinity, but the analog will be considering the minimum of the Boltzmann function. So in H3, that's really the natural projection. If you want to project A onto this total geodesic H2, we want to take the point on which the Boltzmann function is minimum. That is, horosphere is tangent at pi of A. This horosphere based at A is tangent to H at pi of A. So given a point A in FP, we want to find the minimum of the Boltzmann function associated to A restricted to H. So this doesn't depend on the base point. And so we will define omega in FP to be the set of points so that this Boltzmann function restricted to H is proper. So then we have at least one minimum if the map is proper. But actually, Boltzmann functions are always convex in cat0 spaces. And so the point where the Boltzmann functions are not strictly convex are well understood. And it's only when everything happens in a flat. So if we have a vector v dot, so that the Hessian of the tangent at x, so that the Hessian of v dot and the direction v dot is 0, then it means that x, v dot, and a lie in a common flat. So it means that the vector vax based at x pointing towards a is in the same flat as v dot. Okay. So, but sometimes one can avoid this situation, and that's what motivates the definition of P regular. A vector v is called P regular if the Cartan projection of v is never orthogonal to w dot p when w is in the value group. So what we want to ensure is that if the Hessian in the direction of the Boltzmann function in the direction v v is 0, we don't want this to happen, and if the differential of the Boltzmann function in direction v is also 0. So we want this situation to be impossible, because we want the Boltzmann function to be at least strictly convex at critical points. And this notion of p-regularity is exactly what we want, so that this situation cannot occur. Because imagine that this situation occurs, it means that we have in a flat, which we can take as the model flat to the action of G. We have the vector v, which is equal to its Cartan projection if we map it to the model flat. And we have the vector Vax pointing toward A in the same flat. But if V is in SA+, Vax will be equal to W dot P for some W in the Weil group, because A is in FP. And so if we have this notion of p-regularity, this situation cannot occur. And so if the tangent space of S consists of p-regular vectors, the Hessian is strictly positive at critical points. So now I want to say a few words about p-regularity, because it's different from the usual notion of regularity. So in PSL3R, I have this vector P1 and P2 in a SA+. And so being P2 regular means that the Cartan projection is not orthogonal to P2 or to any Weil group translate of P2. So it means that Cartan projection of V is never in the green line, which is the usual notion of regularity, which means that the Cartan projection is in the inside of the Weil chamber. But the notion of V being P1 regular, it's a different notion. And it's equivalent here to having the Cartan projection of V not in any of these dotted lines, which are orthogonal to P1 and its translates. And so this is equivalent to having lambda middle eigenvalue not equal to 0. Okay, so this is a different notion, but still for almost every V, this will be satisfied. So now we're back to our situation when we had our representation into G that preserved the geodesic H2 and acting properly on it. So now if we assume that all tangent space vectors to this surface is p-regular, then the space of points A, so that the Boltzmann function admits a minimum, is a co-compact domain of discontinuity for rho. And so actually I define omega as the space of points so that the Boltzmann function is proper. But actually, if the Boltzmann function is proper, it admits a minimum. And actually, it's unique because the Boltzmann function will be strictly convex at critical points and convex. And also, if we have a minimum, then the function will be proper because, again, Boltzmann function are strictly convex at critical points and convex. And moreover, we have a map pi from omega to H, which at A associates the point on which it reaches its minimum on H. And this is a smooth and rho equivariant vibration. And so this is what we want to apply to understand. So we show that some domain of discontinuity. This shows that some domain of discontinuity fibers over the surface. And but now we want to compare this domain with the domain we had previously for Anosov notations. So before I do this, I want to explain a slight generalization of this result. So we don't need the surface to have an invariant totally geodesic surface. We need something weaker, which is the following. Let P be a choice of a flag manifold in the visual boundary. A surface is called P in the symmetric space, is called P nearly geodesic if for all elements is a flag manifold Fp. The Hessian of the Boltzmann function at direction V is strictly positive whenever the differential is equal to 0. So when S is H3, it's equivalent to having principal curvature in -1, 1. And but more generally, in high-rank symmetric spaces, if S is totally geodesic and perigolar, then it satisfies this property. It is P-linearly geodesic. But what's interesting with this property is it's an open property. If we deform S for the C2 topology a little bit, then it will still be P-linearly geodesic. And so if we have a rotation that admits an equivariant nearly geodesic immersion, U, then, so when I say an immersion is P-linearly geodesic, it means that its image is locally P-linearly geodesic. Then actually rho will be Anosov with respect to some parabolic subgroup. And the domain omega will be one of the associated domain of discontinuity constructed for Anosov notation by Kapovitch, Leeb, Porti. And actually, more precisely, it's one of the domain constructed by Titz-Brewer ideals, and more precisely, by the special Titz-Brewer ideals obtained by metric thickening. And okay, so this omega is really one of the domains constructed by Kapovitch, Leeb, Porti, and moreover, omega fibers over the surface. Over the initial cover of the surface, rho equivalently, so the quotient fibers over the surface. And this means that omega equal omega rho, where omega rho is the Guichard Wienhard domain of discontinuity. For G equal PSL2NR and rho generalized function. So we can apply this theorem, and it tells us that okay, the domain omega rho, the quotient of the domain, fibers over the surface. So now to complete the proof of the theorem I wanted to state, I just need to explain what are the fibers of this projection and why do we get the intersection of two quadrics. So the fibers of the projection, if we have a point X in H, it will be the set of point A in Fp, so that the vector VAX pointing toward A is orthogonal to TXH. So this condition is the same as asking BAO respective to H critical at X, which is equivalent to having a minimum because of convexity condition. So if the flag manifold is, if Fp is Rpn minus 1, then pi minus 1 of X can be actually this condition can be interpreted as the intersection of two quadrics. So TXH is actually a plane generated by two symmetric matrices S1 and S2. And P1 minus 1 of X will be the intersection of the isotropic line for S1 and S2. And so these two, and so we get that pi minus 1 of X intersection of two quadrics. Okay. Actually, doing this construction, we don't get exactly the same two quadrics as with the ones in the paper with Daniel, Alessandrini and Lee. But it turns out that the intersection is still the same topology. Okay, I would like to thank you for your attention. And if you have any question, I will be happy to answer them in the forum or during the office hours.